David Gauci, and it is Tuesday, the 28th of May, 2019, 11:30 a.m. Eastern Daylight Time, 5:30 p.m. Central European Summer Time. On behalf of Dave Nagel and me, I welcome you to the 9th session in the Business and Energy series of Forum 2100. The mission of Forum 2100 is to explore novel ways that business can address challenges of climate change, improve access to affordable energy, and reinforce energy security. This session will run to a tight schedule as follows: 18 minutes of presentation, followed by 10 minutes reserved for questions for our guests to respond to, and you may submit via the chat function at any time any questions that you may have, and then I shall take a minute to wrap up. Today we are very fortunate to have as our guest George Markowsky. George has had a remarkably interesting career. After earning a PhD in mathematics at Harvard, he took a position at the IBM Watson Research Laboratories for 10 years. Thereafter, he transitioned into the academic world, contributing to both the fields of mathematics and to computer science. Among other things, many other things, George has been studying nuclear energy for more than a decade. You can find out more about George's remarkable career posted on the forum2100.org website. Today, George is going to discuss nuclear energy as a solution to climate change, and he will take a rather unconventional approach to this topic. George, welcome to Forum 2100.
Well, thank you, David. Thanks for giving me this opportunity. And I apologize to everybody in advance for talking fast. So let's get started. Here's the, hold on, here we go. Okay, so this is an outline. I think I won't go through the bullets in the interest of time, but this is what I'm going to be covering. So tipping point, you start with a definition. So it's the critical point in a situation, process, or system beyond which a significant and often unstoppable effect or change takes place. It's actually a relatively new addition to the English vocabulary. So what are we talking about? What is going to tip here? And the idea is that our climate is going to tip. And in particular, I'm going to focus on sea level rise, but there are many other things that I can talk about. And actually, I'm sugarcoating this when I'm calling this a tipping point, because I really think that our climate has tipped. And I'll give you some evidence as to why I believe that is the case. And the big question is whether we can recover and how quickly, and in fact, what mechanisms can we use to recover. And some of the issues we're not going to talk about are more frequent powerful storms and having sat through a couple of weeks of tornadoes here in the Midwest. I know what that's all about: droughts, flooding, etc. This could be the future map in the not too distant future of Florida as the sea level rises. There you can see Miami will be well out off the coast. And in particular, not only should we worry about our own country, but if you look at a country like Bangladesh, you can see how many people are living within 5 feet of sea level. Bangladesh is a country now of almost 200 million people. And just think about the thoughts of where those people are going to go. And the official prediction roughly is that sea level is going to rise by 1 meter. This is the Intergovernmental Panel on Climate Change. And if you even look at, if even that's right, go back to this chart and look at where the 3-foot line is in Bangladesh. It's bad enough. But here's a paper just recently appeared in the Proceedings of the National Academy of Science, which is a very prestigious journal, that says that 2 meters by 2100 is not out of the question. And in fact, if you look at the news announcements and stuff, the IPCC has been consistently too conservative in climate change. So what's the picture look like? Well, gee, here's some curves. We're talking about trying to stabilize the climate, and then what do you see? You see essentially rapidly rising usages of energy and carbon generation and all that. And does this look stable to you? And in particular, CO2 emissions have reached an all-time high in 2018. So clearly, you know, all the talk about how renewables are going to change this, that, or the other, we keep setting CO2 emission records. So it's whatever we're doing is not working. And everybody says, oh, you know, the US didn't sign this accord or whatever. Well, lots of people have signed the accords, and you can see what the results are. It's just literally a lot of hot air. So one of the big problems with carbon dioxide and why people focus on it, even though it's not the only greenhouse gas, is the fact that it tends to persist in the atmosphere. So even if you look at this graph here, you'll see that even if we peaked and then started declining here, you could see that the temperature or stabilization would take a few centuries. So that means more meltwater, more expansion of the sea, of the ocean waters. And so this is a real problem. So it suggests that it's not enough to reduce carbon emissions, even if we reduce them significantly. But we probably, if we want to get re-establish control of the Earth's climate, we probably need to remove CO2 in a really major way. And this will take lots and lots of energy. And the big question is, where will this energy come from? Are we going to burn more fossil fuels to remove CO2 from the atmosphere? I mean, that's obviously not going to work. So who are the key polluters? Well, you can see China and the United States. China's already almost twice. Oh, and this is 2015, so I think the chart's much worse. But you can see right up there, and then Germany, the beloved green state, is also one of the main polluters. And in fact, if you collect all of the European Union carbon emissions, they'd probably be between the US and India. So, you know, there's a lot of talk and not much effective action. So CO2 is not the only greenhouse gas to worry about. Methane is another gas. It's important to understand we're running out of buffers. So as the Earth heats up, a lot of the heat's going into the oceans. But that's changing a lot of processes in the oceans. It's affecting the fish. And many of these processes have positive feedback, which means that if you get something appearing, it causes more of that thing to appear. And positive feedback, despite its very positive name, is actually a bad thing. If you want stable systems, what you really want is negative feedback. So if you get more of something, it actually pushes back. And an example of positive feedback is the Earth is warming, it's releasing more methane, which contributes to the greenhouse effect, which creates more heat, which releases more methane. That's what we mean by positive feedback. It's very scary and undesirable. So renewables to the rescue. I think this is a great myth. And I'm kind of very negative about it, because I think we're wasting a lot of time when we really need to get going. And so you read all kinds of crazy things like, we're going to take 43,000 square miles in the Sahara, we're going to build this giant solar farm. And, you know, they seem to not worry about the fact that the night happens every day. And so you're getting no power during the night. And what are you going to do? Run a power line from the Sahara to New York City? The big problem with renewables is they need backup systems. And so these are like alternative energy systems. And the other thing that I find very disconcerting is they constantly talk about capacity, like, oh, this has this capacity, but they tend not to talk about production, about what is actually generated. And in Maine, we've had a very hard time actually getting records of how much power is actually produced by the wind farms. And the interesting thing is that the wind people in Maine are trying to exclude hydropower as a renewable, but when people talk about the contribution of renewables, it includes hydropower. hydropower is pretty much maxed out because all the good hydropower sites have been used up. So here we have another disconcerting curve, which is showing you what's happening with the world energy requirements. And you can see we're not doing at all a good job of reining those in. And here's another chart showing you the contributions up to 2015 of the various sources. You can see renewables kind of growing a little. But if you look at, for example, oil and gas, they seem to be growing just as much. So a lot more work needs to be done. So what is the attraction of nuclear power other than the cute Einstein cartoon there? Well, if you look at the basic equation first brought forward by Einstein, E equals mc squared. And what does that mean? It means that when you convert mass to energy, you multiply the amount of mass by c squared. And since c squared is that number, this is very interesting. You get a tremendous amount of boost. And I'm going to simplify this a little bit on the next slide. And quite frankly, in my opinion, nuclear energy pretty much makes every other energy generation source obsolete because nothing gives you that kind of payback. So how much energy can a penny give you? I like to use this as an example. Well, if you take a penny out in the open market and you purchase energy, you're not going to get very much. But if you take the mass of a penny, just a regular US penny, and convert it to energy, it will give you over 62 million kilowatt hours of electricity worth almost $7 million if you price it at 11 cents a kilowatt hour. And how much electricity is that? Well, it's enough to power 6,000 average homes with electricity for 1 year. It's the equivalent of burning 34,000 tons of coal. I mean, the benefits that come from nuclear power are just astonishing. So let's talk of an ancient nuclear technology. Well, basically, what passes for power generation is like 1940s technology. So if computers still had 1940s technology, this is what they would look like. And you can imagine trying to make a phone call with this or carrying it in your pocket, since a cell phone is really just a glorified computer. And when people talk about the perils or advantages of nuclear power, they tend to be thinking in terms of large-scale, conventional nuclear solid fuel projects such as Chernobyl or Fukushima. I mean, that's all basically ancient technology, and that's what we keep building. One of the things I like to call attention to is the famous Manhattan Project, and this is a timeline, but roughly speaking, in 1942, Oak Ridge was just an empty lot. Los Alamos was an empty lot. In 1943, Hanford was an empty lot. By 1945, we had created reactors, we created nuclear weapons, and we did all that in 3 years in 1940. And I'm going to come back to this timeline. There's been a lot of work done on all sorts of different generations in nuclear power. And in the same way that computer technology has come forward, has progressed amazingly, nuclear technology has also moved forward, but has been hampered by all sorts of political constraints put on it. So we've had 76 years of nuclear fission experience, and we still are doing 1940s technology. We know how to build reactors that are extremely safe. Not only are they extremely safe, but everybody talks about the nuclear waste problem. Well, guess what? Nuclear waste can be used as a fuel. And in fact, nuclear waste is a silly concept, in my opinion, because if you have something that's going to generate energy for 20,000 years, it seems totally unimaginative to bury it in the ground. I mean, you should figure out how to use that energy. And one of the things that I think is really bad about contemporary technology is it seems to be wedded to water. And water is about the worst thing you should get involved in nuclear power, because if there are leaks, it's hard to contain. And that's one of the problems at Fukushima. If you take something like a molten salt reactor, you have liquid, but it's liquid at only at very high temperatures. And if there's a leak, it immediately cools into solid, doesn't get into the oceans or the water table or anything like that. And we know so much more about fission. Idaho Labs has created 87 different types of working reactors. I mean, we're not talking about pie in the sky projects. We're talking about actually working reactors. And modern reactors can come in a variety of sizes. They can be small enough to be launched into space, or large enough to power large cities. They can be built so that you can haul them on the back of a truck, or you can fly them to emergency areas. I mean, it's amazing what we can do. Here are just some of the molten salt reactors that have been built or under construction or under design. There's a tremendous amount of work. And ironically, the US was a pioneer in all of this, and now we're just kind of depending on other nations to carry the work forward. Here's one of the reactors called Krusty. This is a brand new project out of Los Alamos that is building reactors that can be launched into space, that can generate various, a fair number of kilowatts. This is also interesting because computer modeling is playing a big part in creating this reactor and getting it certified. So I think there's a huge role for computer modeling in modern reactor design. Here's kind of a scheme where you can actually imagine, instead of gigantic smart grids, you can imagine much smaller, small town nukes, reactors that are reliable, that can be made so you can't create weapons from them and all that sort of stuff. What about fusion? Well, there are all kinds of articles that have appeared lately about fusion, and the big problem is outside of the hydrogen bomb, no one has produced a fusion reaction that generates more energy than has been put into it. So to think of, I mean, I'm all for fusion, it would be great, but we don't even have one sample of being able to produce controlled fusion power. Now, maybe there'll be a breakthrough and maybe not, but it's probably going to be a while before we get anything. And I think the matter is urgent. I mean, the earth is burning and fission works now. So I think we really need to get going. Just to give you an example of some of the difficulties, here's a talk I attended in 2016 by the director of the Office of New Reactors. And this is the bureaucrats' view of this. Notice they see their licensing procedure as extending from 2016 to 2037. It's 21 years to do the paperwork. We did the whole Manhattan Project in 3 years, and now we need 21 years just to do the paperwork. I think this illustrates exactly what some of the key problems are with our current approach to nuclear. So in conclusion, it is hard to believe we could go from 0 to working reactors and bombs in about 3 years in the 1940s. And now with 76 years of experience in multiple working prototypes, we're still stuck in the 1940s. And the bureaucrats plan a 21-year development of the paperwork to license new reactors. I mean, it's just crazy, in my opinion. We need to do something about this. I think we need to start the large-scale production of modern, safe, and efficient nuclear reactors within the next 3 years. Else our children and grandchildren will have much cause to be displeased with us. And there it is. I think I did it in under 18 minutes.
George, very good. Thank you very much. Let me pose a couple of questions to you just to get sort of started here. You have, there are a couple of things that have come up here, but one of the big issues, it would seem to me, that if you're thinking about choosing any kind of energy system, nuclear or non-nuclear of any ilk, whether it's coal or renewable of any kind, is that the decision maker is always faced with some trade-offs. So you've argued quite passionately for the advantages of nuclear. Are there any things that are kind of showstoppers that kind of stop us or stop society from adopting nuclear? And what are they?
Well, I mean, first of all, society has adopted nuclear. I mean, they're working reactors right now. I think France derives the majority of its electricity from nuclear reactors. I mean, there are obviously issues like, for example, if you go to large scale, you have to worry about fuel for the reactors, how much uranium. There are alternatives. You have to look at things like thorium. So if you can build reactors that use thorium, you can extend sort of the length of time. There are issues. One of the things that I think is important is to avoid the mistakes of the past. I mean, we have almost 3/4 of a century, or actually more than 3/4 of a century of experience with nuclear reactors and the nuclear process, and it's just, we need to build on that. The other thing is that I think has hampered nuclear power is the fact that it was born out of a desire to make weapons. A lot of the 1940s technology is critically tied to weapons production. We really need to separate nuclear power generation from weapons production. And I think that's been one of the key elements that's made it difficult. Nuclear waste, as I said, I think is something we need to think about, but a lot of the new reactor designs can burn radioactive materials. I mean, if you put it into the right kind of reactor, you can reduce its radioactivity tremendously. And so there'd be a lot of technical issues for sure to ramp up and change styles. We have engineering codes that are so antiquated that you can't build anything that hasn't been built before. So I think a tremendous amount of political change needs to be in place, as well as there are technical problems for sure.
So George, you also used the Manhattan Project as sort of the iconic reference point, particularly relating to the timeline. But the Manhattan Project seems to kind of cut two ways, because yes, a lot was achieved within 3 years' time, and it actually is quite remarkable, but the objective was rather narrowly specified. Here, though, if we're not trying to build a weapon, and maybe people were not quite so conscious of some of the drawbacks or the trade-offs that they had to make. We're actually trying to think about nuclear power being presented to civil society for its use, much along the lines of what Dwight Eisenhower argued in his Atom for Peace speech in 1953, I think it was. So today we have things like Hannaford, which is a nuclear waste repository that is suffering from some major operational issues in managing the waste. So is this not suggesting that maybe the 3 years timeline is maybe not a useful or a particularly accurate reference point that we should be thinking about?
Well, to be sure, lots of shortcuts were taken, much to eventual regret. And you're right, it was a very narrow focus. My main point is that you look at what they accomplished in 3 years and what we're planning to do in 21 years, which is just to work through the licensing agreement. I mean, in 21 years, the climate will be so far gone that it's going to be very difficult to do something. And what I think is that we really need to apply the same sort of urgency that was applied in the Manhattan Project to start getting results, because year after year we're setting new records in CO2 emissions. We're not making any progress toward any goals, toward the Paris goals, toward the Kyoto goals. I mean, it's just out of control. And I think if we want to at least try to reestablish some control over the climate, we have to treat this with a much greater degree of urgency. And we have 3/4 of a century of experience. I mean, we know what mistakes they made in Hannaford and Rocky Flats in Colorado and lots of other places, and we should build on that.
So you mentioned, just to shift a little bit, you mentioned in the presentation the advances and actually the history of the molten salt reactors, the liquid fuel reactors, and some of the advantages to them. One of the things that I think I understand you to say is that these are reactors that can be scaled up and down, that can actually be produced at relatively small scale. Is that correct?
Yeah. I mean, but one of the things that was dismaying was when you looked at even a lot of the new projects, they all want to involve water. I think water is like the worst thing that you can bring into a nuclear reactor situation, because if you have a leak, water runs into the ground, it runs into the water table, it runs into the ocean. I mean, it blends with nature. If you're using a medium like sodium and it's liquid at like 800 degrees, when it leaks, it immediately cools and becomes a solid. So the whole cleanup operation becomes much, much easier, and you don't have this kind of trace radioactivity all over the place.
Okay, but let me take another tack on this. I understand what you're saying, which relates, I suspect, to waste management or the environmental consequences associated with conventional nuclear systems that are using water. But if we go back to the molten salt reactor for just a moment and the scaling issue, if you can make the reactor small, this actually would seem to have two kinds of implications. One would be it resets the economics of building nuclear power and distributing it into the economy. So you don't have to, I don't know what it is, invest $50 billion to build a nuclear power plant. You can actually chop that up and risk much lower sums of capital to build power plants that could be distributed and owned maybe by a wider range of users or players anyway. Is this something that actually is being discussed or considered, because it seems to address directly a business issue?
Well, I think it's discussed, but I don't think it's discussed in the mainstream business issue. I mean, utilities tend to be very conservative because of legal requirements, and they're limited to a certain number of types of reactors that have been licensed. And the next to the penultimate slide there shows you that, I mean, the licensing is just a nightmare, and it's just hampering. It's just hampering development. And I mean, people may not like it, but I really don't think there's a choice. I mean, if we're either going to let climate just run wild and live with the consequences, which I don't think are going to be good, or we're going to have to figure out how to make nuclear power work and use it to both reduce drastically the CO2 going into the atmosphere, and ultimately maybe even use that energy to remove CO2 from the atmosphere so that we get to some sort of stable situation, which of course raises lots of political issues. Like if you start thinking of the Earth as having a thermostat that the human race controls, who gets to set the temperature? Okay. Like when you live with someone who likes it warmer or cooler than you do, you always have this kind of negotiation as to where to put the temperature. So I think that most of the problems that we're going to face are going to be political problems, and trying to live as one kind of, as humanity on what I like to think of as spaceship Earth. And at some point, if we're going to accommodate billions of people, multiple billions and even more billions on the way, we're going to have to get a lot more serious about managing the Earth and controlling it, and not letting just things run totally wild.
Okay, so if I'll accept the point that there are political difficulties in trying to implement anything here. So this raises the question, if there is resistance, and there you are sitting in the middle of the United States, and I'm sitting in Europe, and there are others on this webinar who are elsewhere on the planet, where do you think the opportunities are probably greatest, considering the benefits as you articulated them?
Well,
implement nuclear solutions into the energy systems. Is it in the developed world? Is it in the emerging economies? Is it in the least developed parts of the world?
Well, I think the most promising places are the places that are about to go underwater. Island nations like Kiribati that are just barely hanging on, and If they don't do something, they're going to literally be gone by 2100, just completely gone. I think they might be receptive to permitting some experiments that take place on their land. Well, what's remaining of their land. So I think we need to start getting very creative and get very active, because you know, it's really the bulletin of the atomic scientists used to have this clock on how many minutes before midnight, when supposedly World War III. Well, the clock for climate change is already past 12. It's probably about at 12:30.
Well, okay. Unfortunately, George, we're out of time. We will be recording this session. We have recorded the session, and we'll be placing it up on the forum2100.org website. So thank you very much for your questions, everyone in the audience. Thank you, George, for your presentation. I think you've succeeded in making us a little more curious about the opportunities for nuclear power as a tool for addressing the potentially calamitous consequences of climate change as you've described them. And so please, everybody, take the opportunity to visit the website, and you can view the archives there of all of our sessions, including this one. And please pass the word to others you think who might have interest in following the work of Forum 2100. This is the third session of 2019, and please be looking for announcements of future events that we will begin again in September. Dave Nagel and I thank you all for attending the session today, and we wish you all a very pleasant summer. Bye for now.